January 11, 1944, 32,000 feet above Oschersleben, Germany. The outside air temperature reads minus 56 degrees Fahrenheit, 40 degrees colder than the inside of a domestic freezer. The four Wright R-1820 Cyclone engines on a B-17G of the 401st Bomb Group are burning aviation gasoline at the rate of 200 gallons an hour. But that is not the most important fluid keeping the aircraft alive. The most important fluid is the 37 quarts of oil circulating through each of those 9-cylinder radial engines. If that oil fails, the bomber falls. Not in a slow descent, not with warning. The bearings will seize within 90 seconds of losing pressure. The pistons will weld themselves to the cylinder walls. The propellers will stop. The crew of 10 men will have just enough time to discover, in the silence that follows engine failure, that the German fighters they fear most are not the only thing capable of killing them at 32,000 feet. The oil is not failing. It will not fail today. It will not fail on the next mission. It will not fail across hundreds of thousands of bomber sorties flown by the United States Army Air Forces and the Royal Air Force between 1942 and 1945. This is the strangest fact of the strategic bombing campaign, and almost nobody ever tells it. The Norden bomb sight is famous, the Browning machine guns are famous, the Pratt & Whitney Twin Wasp and the Wright Cyclone are famous. The Merlin engine that powered the British Lancaster and the American Mustang is famous beyond description. The fluid that allowed any of those engines to run at all at 50 degrees below zero at 30,000 feet for 10 consecutive hours has no monument, no museum exhibit, and almost no place in the histories. It came from a small refinery town in northwestern Pennsylvania, from a particular grade of crude oil pulled out of the ground in the 1800s, and from a chemistry problem that the United States solved while Germany was still struggling to make synthetic substitutes work. This is the story of that fluid. It is the story of how Pennsylvania crude oil, refined into aviation lubricant, became one of the most quietly decisive industrial achievements of the Second World War. Most people who think about aircraft engines think about cylinders and pistons and propellers. The engineers who actually built them thought about oil first, second, and third. The reason is mathematical. A Pratt & Whitney R-1830 Twin Wasp, the engine that powered the B-24 Liberator, the PBY Catalina, and the C-47 Skytrain, contains 14 cylinders arranged in 2 rows. Inside that engine, the crankshaft rotates at 2,400 revolutions per minute at cruise power, and considerably faster on takeoff. The connecting rods, the master rod bearings, the cam followers, the supercharger gears, and the reduction gearing on the propeller shaft are all metal surfaces moving against other metal surfaces at velocities measured in feet per second and pressures measured in tons per square inch. If those metal surfaces touch each other for even a fraction of a second, the engine destroys itself. The contact temperature spikes above the melting point of aluminum. The bearings gall. The cylinder walls score. The connecting rod throws itself through the side of the crankcase, and the aircraft glides home on 3 engines if it is lucky, and on no engines if it is not. The only thing standing between functioning engine and catastrophic failure is a film of oil approximately 1/10,000th of an inch thick. That film has to survive at engine temperatures that can exceed 220 degrees Fahrenheit inside the crankcase. It has to flow freely at ambient temperatures that, in winter operations over northern Europe or at high altitude over Germany, routinely fell below minus 40 Fahrenheit on the ground and minus 60 in flight. It has to resist oxidation because the air pumped into the engine for combustion also reaches the oil and tries to break it down chemically. It has to disperse the sludge and carbon deposits that combustion creates. And it has to do all of this for hundreds of hours of operation in combat conditions with no possibility of maintenance between takeoff and landing. The British and Americans in 1939 had no production-ready synthetic chemistry that could do any of this. They had a different solution. They had geology. In August 1859, an unemployed railroad conductor named Edwin Drake stood on a piece of farmland in northwestern Pennsylvania and watched his rig strike oil at a depth of 69.5 feet. The find launched the modern petroleum industry. It also launched, by complete accident, the supply chain that would lubricate the Allied air war 83 years later. The crude oil pulled from northwestern Pennsylvania, an area centered on the towns of Oil City, Titusville, and Bradford, turned out to have an unusual chemistry. Geologists classify crude oil by its molecular structure into roughly two families: paraffinic crudes, which are rich in straight-chain hydrocarbons and waxes, and naphthenic crudes, which contain more ring-shaped molecules. Most of the world's oil, the crude that came out of Texas and Oklahoma and the Soviet Caucasus and the Persian Gulf, was naphthenic or mixed. Pennsylvania crude was almost pure paraffinic. It contained almost no asphalt. It carried only trace amounts of sulfur and nitrogen, the impurities that ruin lubricants. It was, by chemical accident, the closest thing to a natural lubricating base stock that existed anywhere on Earth. For 70 years before the Second World War, oil companies had refined Pennsylvania crude into automobile motor oil and sold it at a premium. Brands like Quaker State, Pennzoil, Kendall, and Wolf's Head all built their reputations on the fact that they used 100% Pennsylvania-grade base oil. The Pennsylvania-grade Crude Oil Association, founded in the early 20th century, licensed a registered logo to refiners. The bond they had to post to use that logo was $1,000. Field inspectors checked compliance. Advertisements ran in the Saturday Evening Post. This was all consumer marketing in 1924. It would become a matter of strategic survival in 1942. When the United States entered the Second World War, the question facing the War Production Board was not whether American industry could refine Pennsylvania crude. The refineries existed, the pipelines existed, the labor force existed. The question was whether there was enough of the right kind of oil to lubricate every engine on every aircraft, tank, truck, ship, and submarine the Allied war effort would need. And the answer, alarming when it was first calculated, was no. Bradford, Pennsylvania, in September 1941, was a town of about 17,000 people sitting on top of one of the most productive shallow oil fields in North America. The McKean plant of the Quaker State Refining Company, photographed that month by Alfred T. Palmer for the Office of Emergency Management, dominated the local landscape. The Library of Congress still holds Palmer's negatives. Huge steel tanks, a cracking unit, and a stabilizing tower silhouetted against an autumn sky. A caption written by a government propagandist, surprisingly accurate for once: "Oil for the armies of democracy." The Quaker State Corporation, formed in 1931 by the merger of 19 separate regional oil companies, had been a civilian motor oil business until that point. In 1940, the company had introduced what it called stabilized Quaker State motor oil, a product with improved chemical stability against oxidation. In 1941, it followed with Quaker State HD high detergency oil. Both products had been developed for the civilian automobile market. Both would now be redirected, along with everything else the Pennsylvania refining industry produced, to military specification. The civilian car owner who walked into a filling station in 1942 to buy a quart of Pennsylvania-grade oil found himself looking at empty shelves. The Pennsylvania-grade Crude Oil Association had to contract the Illinois Institute of Technology to investigate widespread mislabeling because civilian-grade oil was being passed off as Pennsylvania-grade in violation of the licensing rules. There was simply not enough of the real product to go around. The military needed all of it. Quaker State alone until 1944 did not even drill its own oil. It bought crude from independent producers around Bradford, refined it, and shipped the lubricants in steel drums and bulk tank cars to military depots from New Jersey to California. In 1944, under wartime production pressure, the company finally bought the drilling facilities of the Forest Oil Company in Bradford to secure its own crude supply.
That single acquisition would eventually account for about 20% of the company's total crude. The Bradford refinery is still operating today. It is the oldest continuously running refinery on Earth. The product it makes is no longer called Quaker State. It is called Brad Penn, and it is still cut from the same Pennsylvania paraffinic base stock the 8th Air Force ran on at 30,000 feet over Germany. The United States military, by 1942, had reduced the entire problem of aviation lubricant to a single document. It was called Specification AN-VV-O-446. Most pilots and crew chiefs never saw it. They knew the oil by its viscosity grade, 1065, 1080, 1100, or 1120. The grade number corresponded to the viscosity of the oil at 210 degrees Fahrenheit, measured in Sabled universal seconds. Grade 1100, the most common aviation oil for radial bomber engines, was the equivalent of what civilian motorists today would understand as a straight SAE 50 weight. It was, by any standard, an extraordinarily thick oil. Modern automobile engines use oil with 1/4 or 1/5 of that viscosity. Aircraft engines needed it thick because the clearances between moving parts in a radial engine were much looser than in a tightly machined modern car engine, and because the operating pressures and temperatures were much higher. Grade 1100 was straight mineral oil, no detergent additives, no viscosity modifiers, no dispersants. It was, in chemical terms, almost identical to the lubricant a 1925 Model T owner would have poured into his crankcase, except that the base stock had been refined to a much higher standard of purity. The reason for the simplicity was not technological backwardness, it was hard-won engineering caution. The Aeroshell Handbook, published by the Shell Oil Company in July 1945 and reprinted in September 1946, addressed the question directly. Detergent additives, the handbook noted, could create combustion chamber deposits in certain engine types. This had specifically occurred with Rolls-Royce engines. For that reason, detergent-doped oils were not approved for any Rolls-Royce engine of the period, including the Merlin. The British Air Ministry recommended what it called Aeroshell 100, a straight-grade, undoped mineral oil refined to the strictest viscosity and purity standards available, with no chemical tricks. The American specification was similar. The military bought oil that did one job extraordinarily well. It lubricated metal against metal at high temperature, high pressure, and high revolution. Everything else, including the cold weather problem that would have stopped the bomber campaign in its tracks, was solved not in the oil, but in the airplane itself. The problem that the engineers at Wright Aeronautical and Pratt & Whitney did not have a chemical answer to was simpler to describe than to solve. Mineral oil, no matter how well refined, gets thicker as it gets colder. A grade 1100 oil that flows freely at 200 Fahrenheit becomes the consistency of cold molasses at 0. At 30 below, it becomes nearly solid. A starter motor cranking a radial engine at 30 below cannot move oil that thick through the lubrication galleries fast enough to keep the bearings supplied during startup. The engine seizes before it ever fires. This was not a theoretical concern. It was an operational catastrophe waiting to happen. Bomber bases at Thurley, at Bassingbourn, at Snetterton Heath, at Polebrook, and at every other 8th Air Force airfield scattered across East Anglia routinely experienced winter mornings cold enough to make engine starts impossible without intervention. American bases in Alaska, where Lend-Lease aircraft were being ferried to the Soviet Union, faced temperatures that made East Anglia look tropical. The solution was a small valve and a switch on the cockpit panel. It was called the oil dilution system. On the last flight of the day, with the engines warm and running at idle, the pilot would activate a solenoid that injected a metered quantity of 100-octane aviation gasoline directly into the engine oil. The gasoline mixed with the hot oil at a controlled rate, typically 1 quart of fuel per minute of activation time. After 2 minutes of cold dilution at oil temperatures below 50 degrees Celsius, the pilot would shut down the engine with the dilution valve still open until the propeller stopped turning. The diluted oil, now a mixture of mineral lubricant and aviation gasoline, would remain liquid through the night even at extreme cold. When the engine was restarted the next morning, the gasoline would boil out of the oil as the engine warmed, leaving the original lubricant behind to do its job at altitude. The Republic P-47 Thunderbolt, the Boeing B-17, and most other large radial American engines all carried the system. The cockpit switch was unmarked and easily overlooked. Pilots who forgot to dilute their oil at the end of a winter mission discovered the following morning that their engines would not turn over. This was not glamorous engineering. There is no chapter on it in most histories of the air war. But without that small solenoid, the brass valve, and the carefully measured Pennsylvania-grade base oil that allowed the system to work in the first place, the 8th Air Force would have lost half its operational days in any given winter month.
A Pratt & Whitney R-1830 Twin Wasp on a B-24 Liberator did not just need oil, it consumed oil. The standard engine oil tank for each of the 4 engines on a B-24 held approximately 40 quarts. The engine, under cruise conditions, consumed oil at roughly 1 quart per hour. On a long mission to a target in Germany, an 8 or 10-hour round trip with combat power required for the run over the target, an aircraft might burn through 5 or 6 quarts per engine. With 4 engines, that meant a single B-24 mission could consume 80 to 100 quarts of aviation oil. The 8th Air Force, on a full-strength operation, might launch 1,000 heavy bombers in a single morning. The arithmetic produces a number that strategic planners had to calculate for every operation. A 1,000-bomber raid burned approximately 100,000 quarts of aviation oil, or 25,000 gallons. Sustained day after day across a strategic bombing campaign that lasted from 1942 to 1945, the cumulative demand ran into the tens of millions of gallons. The reason for the high consumption was not engine wear, though that was a factor. It was design philosophy. Radial aircraft engines deliberately used a loss lubrication approach in which a portion of the oil was burned in the combustion process, blew past the piston rings, or escaped through breather vents during the violent pressure cycles of high-altitude operation. This was considered acceptable, even desirable, because the constantly replenished oil supply meant that contaminated oil never built up to dangerous concentrations. What the design philosophy demanded was a supply chain capable of delivering enormous quantities of refined lubricant to forward airfields without interruption. Steel drums of aviation oil moved by train from Pennsylvania to East Coast ports, by ship across the Atlantic in convoys that were themselves protected by the very air power the oil enabled, by truck and rail from British ports to scattered airfields, and by hand from depot trucks to individual aircraft hardstands. Every single quart had to arrive on time, at the right specification, properly stored, and uncontaminated. The crews who handled those drums called them the iron rations of the air war. They were stacked 5 deep along the perimeter tracks of every operational airfield in East Anglia. They were, in quiet aggregate, more strategically important than the bombs the aircraft carried. While American industry was solving the problem with Pennsylvania paraffinic base stock, Germany was solving it with chemistry. The reason was simple. Germany did not have Pennsylvania crude. Germany did not have meaningful access to natural petroleum at all. Its small Hanover fields could not produce a fraction of what the Luftwaffe needed. Every drop of crude oil Germany did not import from Romania, the only major European petroleum source under Axis control, had to be made out of coal. The man tasked with creating a synthetic alternative was a German chemist named Hermann Zorn. Working from the 1930s onward at the laboratories of IG Farben, Zorn led a research program that evaluated more than 3,500 distinct ester compounds between 1938 and 1944. The goal was a synthetic base oil that would behave like petroleum but could be manufactured from coal-derived chemistry.
Zorn's program produced diesters and polyol esters that, in pure chemical terms, were superior to natural mineral oil in several respects. They had higher viscosity indices, which meant they thinned out less at high temperature. They had better cold flow properties. They resisted oxidation more effectively. They left fewer combustion deposits. The synthetic oils Zorn developed were used in the Messerschmitt Bf-109, in the Focke-Wulf Fw-190, and in the Junkers U-87 Stuka. They were called Hochtemperaturöl. They worked. In some respects, they worked better than the Pennsylvania-grade oil the Americans and British were using. But the German synthetic program had a fatal weakness. It was expensive. Production was slow. The plants that made synthetic lubricants were the same plants, often physically adjacent to the same plants, that made synthetic aviation gasoline and synthetic rubber. They were targets. The Allied oil campaign, beginning in earnest in 1944, hit IG Farben's synthetic fuel and lubricant facilities relentlessly. By February 1945, German production of aviation fuel had fallen to about 0.5% of the production rate of early 1944. Lubricant production followed the same curve. The Americans had paraffinic Pennsylvania crude, refineries thousands of miles from any bomber, and a transportation network protected by the Atlantic Ocean and the United States Navy. The Germans had chemistry. In a long war, the geography won.
While Pennsylvania crude was carrying the lubrication burden of the actual war, the American military had not abandoned synthetic research. The work was simply being done with less urgency, on a smaller scale, and with a different objective. Between 1942 and 1945, a chemist named W.A. Zinsman led a program at the Naval Research Laboratory in Washington that paralleled Zorn's German work. The Americans had crude oil. They were not trying to replace it. They were trying to understand what came next. Zinsman's program produced the first American diester base oils. These were not deployed in any combat aircraft of the Second World War. The mineral oil supply was adequate, the specifications were proven, and there was no operational reason to introduce a new lubricant chemistry in the middle of a war. The diesters went into laboratories, into test stands, and into the technical literature. The reason this matters is that within 5 years of the war ending, those same diester chemistries would become the foundation of synthetic lubricants for the first generation of jet engines. The early turbojets, with their internal operating temperatures of 450 to 550 degrees Fahrenheit and their requirement for lubricant fluidity at extreme cold, could not run on mineral oil. They needed exactly the kind of synthetic chemistry the Germans had been forced into and the Americans had quietly developed in parallel. When Lieutenant Colonel Al Amatuzio, a squadron commander in the Minnesota Air National Guard during the late 1940s and 1950s, observed the performance of synthetic oil in his squadron's early jet aircraft, he was looking at the direct technological descendants of the Naval Research Laboratory Wartime program. He would later found the company AMSOIL, which introduced the first synthetic motor oil for civilian automobiles in the United States in 1972. The Pennsylvania-grade mineral oil that won the strategic bombing campaign of the Second World War was, by 1972, already obsolete in the most demanding aviation applications. But for the engines that mattered, in the war that mattered, it was what flew.
The numbers on Allied bomber engine reliability are difficult for modern readers to comprehend. A Pratt & Whitney R1830 Twin Wasp, installed on a B-24, had a designed time between overhauls of approximately 600 hours under combat conditions. A Wright R1820 Cyclone on a B-17 ran similar intervals. Under sustained combat operations, with multiple full-power climbs to altitude, extended cruise at high settings, combat maneuvering, and the cold soak of hours at 30,000 feet, those engines were expected to run reliably for what was, in 1942 engineering terms, an extraordinarily long service life. They did.
The B-24, currently flown by the Collings Foundation, an aircraft named Witchcraft that performs at air shows across the United States, is powered by 4 Pratt & Whitney R1830 engines. They were built more than 70 years ago. The pilots who fly the aircraft today, including Jim Harley, who has flown it for the Foundation for a decade, describe the engines in identical terms to the men who flew them in combat: loud, cold, uncomfortable, reliable. The aircraft's chief gunner during its wartime service, Russell Jones, who flew 50 missions in B-24s, remembered the engines for one quality above all others: they kept us going all the time. This is the quiet aspect of the lubricant story that the engineering specifications miss. Reliability is the product of dozens of separate engineering decisions, but it begins with what flows through the engine. The bomber crews who flew over Germany did not lose engines to oil failure. They lost engines to flak, to fighters, to combat damage, and to mechanical wear at predictable rates. They did not lose engines because the lubricant gelled, broke down at high temperature, oxidized, or failed to maintain its film strength under combat load. The oil simply worked. It worked in the heat over the target. It worked in the cold above the contrails. It worked at low altitude on emergency landings with 1 engine on fire and 3 engines straining. That kind of reliability is what makes a strategic bombing campaign possible at all. Without it, the 8th Air Force is not a strategic instrument. It is a series of expensive accidents. There is a record buried in the technical files of the United States Air Force's Material Command that captures the contrast precisely. Captured German aircraft engines examined by American engineers in 1944 and 1945 showed an unusual pattern. The synthetic ester lubricants Zorn had developed performed superbly on test stands. They were chemically more advanced than the American mineral oils. But the engines themselves told a different story. German aircraft engines recovered from crash sites and abandoned airfields in late 1944 and 1945 showed signs of oil starvation, of contaminated lubricant, of running with substitute oils when the proper Hochtemperatur oil was unavailable. The Luftwaffe, by the final year of the war, had aircraft with first-rate engineering and second-rate operational fluids. The bombing of the synthetic plants had broken the chemistry. The bombing of the rail network had broken the distribution. The bombing of the airfields had forced dispersal to improvised facilities that did not have proper lubricant storage. A Messerschmitt Bf 109 of late 1944 was still a formidable aircraft on paper. In practice, its engine, lubricant, and fuel were all degraded versions of what its designers had specified. Maintenance records of the period, recovered after the war, describe Luftwaffe ground crews mixing different oil grades, reusing drained lubricant after rough filtration, and operating engines on what amounted to whatever fluid was on hand. The American bomber crew taking off from Snetterton Heath at 6 in the morning in January 1945 was operating on something completely different. The drums stenciled with specification ANVV0446, grade 1100 that the ground crew had used to top off the oil tanks, were identical to the drums used the previous week, the previous month, and the previous year. The base stock had come from Pennsylvania Crude, refined in Bradford or Oil City, or one of half a dozen related refineries operating at maximum capacity. The viscosity was the same, the flash point was the same, the pour point was the same. The bomber that took off from Snetterton Heath could expect the same engine performance, mission after mission, as a function of nothing more glamorous than industrial consistency. That consistency is what the Germans could not match, not because their chemistry was worse, but because their geography, their industry, and the air war they were losing had made consistency impossible. When the war ended, the men who had refined and shipped the lubricants of the Allied air campaign went back to selling motor oil for civilian cars.
Quaker State expanded its drilling operations and pushed into 13 Midwestern states through its distribution agreement with Standard Oil. Pennzoil grew into a national brand. Kendall continued to ship from Bradford. The wartime contracts wound down. The drums stopped moving by the millions. The aircraft engines those lubricants had kept alive were retired one by one through the late 1940s and 1950s, replaced first by larger and more powerful piston engines like the Pratt & Whitney R4360 Wasp Major, and then by jet engines that ran on a chemistry the wartime mineral oils could not service. The Pennsylvania paraffinic base stocks gradually lost their market position to crude oil pulled from new fields in Texas and the Middle East, then to chemically engineered synthetic base stocks that required no particular crude source at all. The Bradford refinery is still running, the oldest continuously operating refinery on Earth, now owned by American Refining Group, still produces Brad Penn engine oil from 100% Pennsylvania-grade crude. It is a niche product today, used mainly by builders of high-performance and vintage engines who value the particular chemistry of the original paraffinic stock. The volume the refinery produces in a year is a small fraction of what flowed through it in any single month of 1944. The bombers are mostly gone. The B-17 Memphis Belle sits at the National Museum of the United States Air Force in Dayton, Ohio. The B-24 Witchcraft still flies. The R-1830 engines on her wings run today on modern Aeroshell W-100 oil, a direct chemical descendant of the wartime Grade 1100 specification, refined according to standards the wartime engineers would have recognized immediately. The men who flew those aircraft are almost all gone now too. Russell Jones, the tail gunner who described the Pratt & Whitney engines as damn good, is among the last of his generation. The mechanics who serviced the engines on the hardstands, who diluted the oil at the end of winter missions and pulled drained crankcase samples to send to Ware Metal Laboratories, are gone with them. What they left behind is not a monument. The lubricant that kept the strategic bombing campaign airborne has no equivalent of the Norden bomb site at the Smithsonian, no equivalent of the Memphis Belle at Dayton. It exists in a quiet way, in the chemistry of every modern aviation oil that traces its specification back to wartime work, and in the fact that the war ended when it did, the way it did, partly because the engines kept running. The British and the Americans had paraffinic oil. The Germans had synthetic chemistry. Both worked, only one of them in the end kept arriving in steel drums at the right airfields at the right time. That is the difference between winning and losing a war fought from 30,000 feet, and it is a difference written into the molecular structure of a particular grade of crude oil that an unemployed railroad conductor named Edwin Drake happened to find under a Pennsylvania farm in 1859. If this kind of unsung industrial history interests you, the kind of story that does not make it into the standard accounts but quietly decided the war anyway, like the video and subscribe. The men who refined Pennsylvania crude into the lubricant that kept Allied bombers flying, the ground crews who handled those drums, the mechanics who calibrated the oil dilution systems on freezing English mornings deserve to be remembered too. War decides what flies. It also decides who refines what flows through the engines.